Okay. So today we'll do something quite different. We'll do local methods. But first, let me wrap up some of the loose ends from a previous lecture. In particular, I want to consider the specific case where we have linear functions, hyperplanes. And so for that, I'm going to take a class F to be the class of linear functions indexed by W, and the norm of W, the L2 norm of W, is just bounded by B. Okay, so that's a ball of radius B. So the class of functions F is a class of functions whose W is bounded by B. Okay? And I'm going to assume that the x's are also in a unit L2 ball, just for simplicity. In that case, we can show that the Rademacher averages of this class are bounded by B over square root of n. So let me just do this quick calculation. And I want to point out that this is quite different from the case where we considered Rademacher averages of the L2 ball. Because the Rademacher averages of L2 ball, the L2 ball was the projection of the class of functions onto the data, right? But actually, if you take these functions which are indexed by the L2 ball and then project them onto the data, I don't know what that object is, right? It's some kind of a polytope, I guess, or something that has a form that's difficult to describe, right? So that's something worth mentioning. And yet the bound that we're going to get is actually the same, and that's just a coincidence. The bound that we're going to get is 1 over square root of n. In this case, you can think of this as a coincidence. Let me write it out. So r hat of f projected onto x1 through xn is just the expected over epsilon 1 through epsilon n maximum. So what are the functions f? They're indexed by w, w bounded by b, of 1 over n. And now I'm going to expand this inner product as epsilon I, the function values on the data, right? So the function values on the data is just the inner product of w with all the data points. Right? So I get epsilon I, w, xi. Right? That's just the definition of these Rademacher averages in this case. But I can take w out by linearity, and that's equal to expected over epsilon 1 through epsilon n max over w bounded by b, L2 norm, of w and 1 over n sum of epsilon I xi. Okay? So this calculation is similar to what we did before when we looked at Rademacher averages of the L2 ball. But now we have these xi's, which are vectors. Before we didn't have that. We just had a vector of epsilons. Now it's a little bit different. But again, the analysis is the same. So we get that this is a definition of a dual norm. Okay, I can pull the scaling b out and just have this w bounded by 1. So I get b times expected over epsilon 1 through epsilon n norm 1 over n sum epsilon I xi. Okay, that's the L2 norm, the Euclidean norm. So what's the meaning of this? Xi's are vectors, and what I'm asking is, I'm going to hit each vector with a plus or minus 1. So I'm going to take either the actual xi or minus xi. Then I'm going to average them, and I'm going to look at the norm of that. Right? That's the meaning of this. And using the trick that we had before, I square and take a square root. I haven't changed anything. Then I use Jensen inequality to pull the square root out. I get expected epsilon 1 through epsilon n norm now squared. Let me pull out the 1 over n. So that comes out as 1 over n. And then I get a sum of epsilon I xi squared. And now I'm good to go because I can expand the square. All the cross terms get annihilated by this expectation. And I'm left over with the norms of xi's squared. So this expression is just the sum of the norms of xi squared. And I assume that the norm of xi is bounded by 1. So I get a sum of, at most, n 1s. That's n. And I take square root. So I get b over n times square root of n, which is equal to b over square root of n, which is what I claimed there. Okay. Now, if b is equal to 1, that's a unit ball, or functions indexed by unit ball. And actually, the answer is the same as if you took the Rademacher averages of the unit ball itself. But it's important to recognize that these w's live in some d-dimensional space. And before, a couple of lectures ago, we considered a b2n, which is a unit ball in the n-dimensional space. So we assume that this is the projection that is the unit ball. But this being the unit ball doesn't mean that the projection is a unit ball. Okay? It just happened that in this case we get the same result. But if you take this norm to be, let's say L infinity, or sorry, let's take L1 norm. Remember the Rademacher averages were 1 over n. Now you're not going to get that. You're going to get something that depends weakly on the dimension, square root of log d over n. I put that calculation in the notes. You can do it as a homework offline. Okay.
So are the xi's units norm?
Yeah, so I assume that xi's are unit norm. Yes? No, this restriction, right? This was our notation for a restriction of the class to the data. The last statement is that if we take this with a L1 norm, and let's bound xi's as L infinity norm bounded, just so that it's dual, they're dual to each other, then this calculation will give us square root of log dimension over n. So it will be a dimension-dependent average. Okay.
Does that mean that xi's are orthogonal?
No.
No,
No, xi's are fixed. Why do we need orthogonality?
what if they point in the same direction? What would be the...
Doesn't matter, right? So when we open this up, what's important is that the cross terms are getting killed because of the epsilons, right? That produces the orthogonality that you need. The orthogonality is not coming from the x's, but from the epsilons. Okay? What is important to realize is, well, this is probably the simplest case of a class of functions that you can try to analyze. And a couple of lectures from now, we're going to replace this with neural networks, multi-layer neural networks, and we'll do pretty much this type of analysis, but a little bit more complicated. Okay? Just a bit more complicated, not too much. I just want to draw your attention to the fact that a couple of lectures ago, we put different sets here, and now we finally got to analyze a set which is coming from the restriction of the class onto the data, which is what we need for uniform convergence. Right? And now the second thing to realize is that if you take the signs of f as the class, not the f itself, but the signs of f, signs of the hyperplanes, then when you look at the projection onto the data, the bound that we're going to get is something that depends on the VC dimension of the hyperplanes, which we already discussed. That's a square root of d. So you get something like square root of d over n. And this heavily depends on the dimension, and it becomes vacuous. You can also get a lower bound for specific x's. this behavior becomes vacuous if dimension is high enough, if dimension is higher than n. So when you look at signs of hyperplanes, when dimension of the space is larger than the number of data points, you can realize all the possible sign patterns. And as we discussed before, the Rademacher averages are then vacuous because this is the whole hypercube, or it can be a full hypercube. So the result about Rademacher averages of the sign of f, in this case, depend on the dimension. The Rademacher averages of the class itself do not depend on the dimension. They're dimension independent. Okay? And this is important. So historically, first it was found in the 60s that there are, well, so analysis didn't go through Rademacher averages, but the results still appear that you can get performance of an empirical minimizer, which depends on the dimension. And you can also get a performance based on the perceptron, or a generalization of perceptron that depends on the margin. It doesn't depend on the dimension itself, right? So how does the margin appear? Well, we did that last time. So the direct analysis of empirical risk minimizer would give us the out-of-sample performance for the empirical minimizer. If all you know that you separate the data the best you can, right? Then that's bounded by, in relation to the best out-of-sample performance of any hyperplane, that scales, and when I put a squiggle, that's up to a constant. I'm skipping constants. The leading term is the Rademacher averages of the sign of f. Okay? So this has to be dimension dependent. This has to be dimension dependent. So the result is vacuous as soon as the dimension is higher than the number of data points. But since we know that we had, a long time ago, we had generalizations of perceptron to high dimensional spaces using the kernel trick, right? The kernel machines. This would be useless in that case. But then what we did last lecture is we presented a margin analysis, which I just want to contrast. The expectation is not important. Let me erase this. So I'm going to be a little bit vague here by putting some additional terms here that take care of the concentration. But what I want to contrast is this is 1 over gamma, the margin, but then you get Rademacher averages of the class itself. And here you go after Rademacher averages in the classical analysis, Rademacher averages of the sign patterns induced by the class of functions. So these are two analyses. They're not, one is not always better than another, but there are regimes when this is non-vacuous and this is vacuous, in particular when dimension is high enough. So let me just remind you what we've got is for any W in the class, the out-of-sample performance is bounded by the proportion of margin errors, and hopefully that's small, plus 1 over gamma Rademacher averages of the class itself. And so if you follow this definition, if you go with this class, then that scales as b over square root of n. So what you get is something that depends on the gamma number of errors plus b over n. And if the data is separated by margin gamma, then you really get something very much like perceptron, except a slower rate, and there is a reason for that. Instead of 1 over gamma squared 1 over n, you get 1 over gamma 1 over square root of n. And with a little bit more work, you can actually replace this. So it can be by the norm of W itself. So for any W, you get a result that depends on the actual norm of, instead of B, so this should point to B. You get norm of W divided by square root of n. And of course you can, if you're actually minimizing margin errors, if you're going after this objective, then you can say, well, my W, that I get W hat, which minimizes this margin number of errors, the empirical performance is better than the margin errors by the W star, so you can pass to W star, as we did before with the empirical risk minimizer, and get a result of a similar flavor with psi here. Okay, but this result holds for all W. Okay, so even if you don't get the details, I just wanted to clarify that you do get two different analyses. One is a more classical analysis that depends on the VC dimension of the class when you're stuck with sign patterns of the class. And that has to depend on the dimension. For neural nets, this would have to depend on the number of neurons, for instance. So this type of analysis for neural networks has to depend on the number of neurons. But this type of analysis depends on the Rademacher averages of this class as a class of real valued functions. And that doesn't have to depend on the dimension. It can depend on the norms of the layers in the neural network. And that's what we're going to do a couple of lectures from now. Okay? Questions? Gamma margin? Just a proportion, 1 over n, proportion of yi w xi less than gamma. Proportion of gamma errors. This is, remember the definition of the, we had several loss functions, this one, then this one, and then this one, right? So this psi is this one. Okay?
You say when cases in which they work in terms of, reasonable bounds in practice, like for neural networks as opposed to different sectors.
So what
This is the theory. Do they work in practice?
well, so they suggest what to do in practice. So what I think Tom is alluding to is there are results, including some that Tommy will discuss, that when you do optimization on neural networks, you do converge to a solution that tends to maximize the margin, okay, under certain conditions. And then kind of a theory does guide you to what you should be doing, right? It tells you that you should be maximizing the margin subject to not blowing up your complexity or not blowing up the norm of your W, right? You can always scale your W, and this will increase linearly, but then the meaning of gamma will also scale in the opposite direction. So just by scaling, this doesn't change, this term. And of course, none of these terms scale just by rescaling. So the whole trick in neural networks is to see whether by, not just by scaling, but by also turning during the optimization procedure, that you can increase the margin, but not just by scaling, but by keeping the norm relatively small. That's kind of gets a little bit maybe ahead of my. Maybe I should stop here. We'll have a couple of lectures on neural network.
Like the normalization thing, maybe, I mean, intuitively. Not normalization, I mean the regularization.
That's right. Let me stop here because I think that these are all valid kind of comments, but I want to go on with local methods. This is just wrapping up the kind of the conclusions from the previous lecture. Okay. All right. So let me step back and say that remember our goal. Our goal was to find an algorithm f hat, find a way to construct f hat from the data such that for the problem that you have, expected out of sample performance of f hat minus L of f star is small. Okay, that's our goal. We know that this is an irreducible number. So that's the best you can do. That's the base error, the best you can do with any measurable function. And we hope to approach that performance quickly with a number of data, okay, small as n increases. That's our goal in this kind of half of the course. And what we've done so far is we said we can't go after this goal immediately all at once. So we're going to separate it into expected L of f hat minus minimum L of f over some class. Or let me do it a shorthand. So this is if you remember our notation, this was a L of f sub capital F plus L f capital F minus L of f star. Okay, that was our way to break up this problem into two parts. This is the estimation error, and this is the approximation error. And loosely speaking, you can think of this as a bias variance decomposition, where this is the bias due to not taking the model that contains f star. Okay, you take a smaller model that makes your algorithm. You're working now with a set that might not capture f star, that introduces a certain bias, but it reduces the variance, right? So once again, if the problem is simple, like perceptron, you might be able to just do the unbiased procedure, which is go after this right away. However, for more complex models, it's very often the case that you introduce bias in hopes of reducing variance. Right? This is a generic statement in statistics. You don't want to do an unbiased procedure. You introduce a bias and hope to reduce the variance in doing so. So again, this is the bias, this is the variance. And
The expectation on that first term?
yeah, so this is the kind of this is over data, and I can remove this and just talk about high probability version of this as a random variable. This is a random variable in the data, so I have to put something. Same thing here, right? This is a random variable, so this whole thing is a random variable. So I put plus blah 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 here, that will quantify the randomness, the deviations. Okay. So today, the loss function is going to be square loss. So L of f of x comma y is going to be f of x minus y squared. And for this loss function, I'm going to introduce a different bias variance trade-off. Not this one, but something more, something that's studied in statistics. For this loss function, I can rewrite our goal. I can rewrite the goal as the expected over the data set f hat of x minus y squared, right? This is the over the data set and the xy pair. That's our prediction loss on a new data point, averaged over the data set, minus the minimum. But you know that the minimum in a regression problem is achieved at the conditional distribution of y given x, the regression function. So I can just write f expected over xy pair, f star of x minus y squared, and I want this to be small, where f star is the conditional distribution of y given that x is equal to x. Okay, so that's that's definition of f star of x. Any question about this? Right, we've done this before. So, yes? Yes, loosely speaking. Why is this variance? Yeah, so it's not precisely the variance, but it plays the same role in terms of the kind of the naming bias and variance. It's not exactly the variance, yeah. Let's call it estimation error. But I still want to put them on the same whiteboard because it's useful to understand that this is one way of doing it, and I'm going to present another way of doing it, okay?
F hat, just remember something. F hat is in capital F, right?
Here, yes. Typically, what you will do is you'll say, once we've done the split, I'm hoping that this is small and I can go ask a mathematician to tell me how close is this class to that. And here, it's natural that you're just going to minimize the empirical risk over the class capital F, and so this will be the empirical minimizer. But the split is correct regardless. So once you do the split, it is natural to minimize the empirical error over the class. Okay? So continuing this point, I want to actually write this in a slightly different way. So I'm gonna continue with the equality. Equal. And I'm going to rewrite this expression. I just want to rewrite this expression. So what I'm going to do is I'm going to take f hat of x. Now I had minus y, and I'm going to stick in the middle, I'm going to stick the f star of x plus f star of x minus y squared minus expected f star of x minus y squared, right? I haven't changed anything. This is equality. Yeah? And now what I'm going to do is I'm going to treat this as a, this is as b, and I'm going to open square. A plus b squared is equal to a squared plus b squared plus 2a times b. Right? Now, b squared is going to cancel with this. Yeah? So this is gone, and the b squared is gone. So I'm left with a squared f star of x plus 2 expected f hat of x minus f star of x times f star of x minus y, close the parentheses. Everyone is with me? I still haven't specified what f hat is. This is genetic. This will work regardless. I claim that this is 0, that this term is 0. It gives me pleasure when such complicated terms drop to 0. It's very satisfying, right? So why is this 0? Sometimes you just wish that it's 0. And often if you wish hard enough, it becomes 0. So why is this 0? Well, there's something called the tower property of expectation. So expectation, this is expectation over the data and the pair x, y, right? So now let's condition on s and let's condition on x. And only look at the expectation over the y variable. Okay? So conditionally on the data set and x, this is a constant that doesn't depend on y. How about this? Well, this is the mean of that by definition. Conditionally on x, the mean of y is f star. I just wrote it here, right? That's the definition of f star. So that is 0. So everything becomes 0. Right? Everyone is okay? Right. So this is equal to expectation of f hat of x minus f star of x squared, where now there is no y variable. The expectation is over the data set, which of course has the y variables, right? X's and the y's, the data set, and the x. Okay? Now, I can write this as maybe a little bit simpler to understand. I expected over s. So what is the expectation over the x variable? Well, let me just write it as the integral of f hat of little x. That's a dummy variable, little x. F star of little x squared p dx, right? That's the definition. So I'm over some space x. I don't specify what the space is, but it's just an integral of the square of the difference when you go over all the x's. Okay. So, conclusion for square loss, the expected L of f hat minus L of f star, which is our goal, is equal, I haven't lost anything, the expected f hat of x minus f star of x squared s and x, right? Now, if you look at this definition, what it is the following, just pictorially. This is f star. Yeah? That's the mean of y given x. F hat is some other function that you created. You take a neural network, that's a function. You take a kernel machine, that's a function, right? You train it with data, and you get some other thing, right? So that's f hat. And what this is doing is it's measuring the square distance between these functions in this way. So looking at every little x, squaring the distance between these functions, and then integrating over the x with respect to the distribution that generated the data, the x, right? So if there is some part of the space here that there is no support, there is a hole, there is no, you never see x's from here, right? So there are some certain images, let's say, that you never see, right? They're just not natural. Then you don't care how close f star is to f hat, right? You only care about closeness where there is enough mass of the distribution of the x. This makes sense.
This is just one given.
And that's actually any f hat. Whenever you have square loss, this is always true. So all I'm saying is the goal that we set, the prediction error, in terms of square loss, is equivalent to this
Yeah.
for any f hat.
This in your picture, f hat here, is just one example because you need to consider all the f hats for different samples.
That's correct. So f hat is a random function. That's correct. F hat depends on s. And so that's why we do it on average over s. That's right. Right. So what this says is draw the data, compute your f hat, which you can now do once you draw the data, and now look at how close these two functions are. Make sense? So in fact, this is just a definition, when you take expected over x of this quantity, that's just a definition of a norm squared. F hat minus f star squared, and with subscript L2 p, or px, the marginal distribution of x. Right? I can write p sub x here, but it should be clear that this p is the marginal distribution of the x variable. Right? So this is the norm squared. Norm squared. Right? Hopefully for some of you this is clear if you've taken analysis. Hopefully this is not too complicated. All right. Now, I can also swap this integral and the expectation, right? So this expectation is also an integral. It's just integral 2n times, right? Because there's n x's and n y variables, so it's 2n integrals here. But I can swap them. I have another expression, which is an integral over the x variable expected over s f hat of little x minus f star of little x squared p dx, right? So what this means, this has a slightly different explanation, which is actually related to what was noticed now, is that the red one is a random function. That's the output of the algorithm when it's fed with training data. So the red curve fluctuates, and actually it's not clear what the mean of that red curve is. It's not fluctuating around f star necessarily. That's something that you would need to prove for a particular algorithm, if that's true. Typically it's not. But what this is saying is, let's measure for the given x, for this given x, on average over the data set for this given x, what is the square distance, right? That's the meaning of that, and then average over the x. Just a different way of interpreting this. So this is often called a risk at fixed x, and this is called the integrated risk. Okay. All right, but let's come back to this to this expression. Remember a while back when we just started, I said that there could be different objectives in learning. One objective could be prediction. I want to predict the y variable given the x variable. I'm going to learn from the data the relationship between x and y. I'm going to try to predict. Another goal could be to estimate parameters or to estimate the function itself. And now you see that for square loss, these two objectives are the same. The goal, the problem of estimating the regression function in this particular norm is the same as the goal of prediction with square loss. So if someone says, I work on prediction, I don't care about estimation, well, you can't, right? Because for square laws, they're the same things, right? Estimation, if there's anything you take out from today, estimation for square laws, the problem of estimation is very closely related to the problem of prediction. In fact, it's if you take the norm to be L2P or Px, then it's the same. The problem is the same, okay? That's clear?
So by estimation, you mean what? Minimizing the norm?
Yeah, the getting close, right? You're trying to get close to this function, right? That's all I'm saying. Right.
Isn't it always, in some sense?
It's not clear, right? Because when we're doing the other approach that I put here, and you're minimizing empirical risk with respect to some, let's say, hinge loss, it's not clear that I'm estimating anything, and I'm going after a prediction error. But it just happens that if you do that for a square loss, then these really are the same problems, right? And it's often the case that once you realize something like this, this opens at least the set of tools that is used in estimation should now be available if you care about prediction, right? That's why the field of statistics, non-parametric estimation, is very closely related to the field of statistical learning, which is about prediction, right? These two fields are really overlapping. So you can't know one and not care about the other. Okay, so what I'm going to do now is I'm going to take this as a starting point and do a different bias variance decomposition, not the one that's based on approximation estimation, but slightly different. So I'm going to take this.
What about other loss functions? Is the square loss the only one?
It's the only one for which this equality holds, right? Right. So, yeah. Well, I mean, I don't know if it's if it is the only one, but so if your y variable is binary, then things simplify. So sometimes the square loss is just equal to some other loss function because the y variable is plus minus 1. Okay. So I actually kind of building on this point that Tommy raised. If I want to do classification, if I care about classification, my y variable is plus minus 1. I could just think of this as a regression problem where I'm trying to go through the or learn the regression function, right? And then take the sign, and that's called a plug-in estimate, for the classification. Okay, so I want to take our kind of our goal minus f star. So this is L2 of P with that definition. And I'm going to add and subtract another quantity, which is f hat minus expected f hat plus expected f hat minus f star. And the meaning of that is, remember the point that we were discussing just before, that red line, that's a random function, and the question is, how close is it to f star? Well, how about the average of that red function, right? Can we at least show that that's close to f star, right? So that's the average of f hat. Except I really need to be careful. I should specify average over what. So I could take this as average over the data, S. That would be the true meaning of that, the average of that function. Instead, what I'm going to do is something else. I'm going to condition on the x1 through xn and only take the average over the y variables. So in this picture, let's say I've got x1 up to xn, and I've got a certain values of the y variable, and I get this red line. Now I'm going to hallucinate what would happen for these same x's if I draw a different set of y's from the same y given x, right? So what I'm essentially doing is this expectation is, let me do it in red. What this expectation is really over y1 through yn, y1 through yn. And I should really write it conditionally on x1 through xn, but hopefully this is clear. Yeah? Okay. Now, you see a plus b squared. You're itching to do what? What you were told in 5th grade. A plus b squared is a squared plus b squared plus 2ab. So let's do it. And I'm going to skip the 2ab. I'm just going to write it as expected f hat minus expected f hat squared. Again, this is a L2p plus expected f hat minus f star squared. Again, this is L2p. So why is the middle term 0? The cross term. Anyone can tell me? Why is the cross term 0? Is 0, exactly. So conditionally on x1 through xn, when you look expectation over the data set, or over the y part of the data set, this is the mean of that. And so the expectation is 0, right? Again, we're happy. This is the bias variance decomposition that is different from the approximation and estimation decomposition. This is called the variance term. And this is the bias, or the bias squared, to be precise, bias squared. Again, the meaning is what we discussed before. On average, my output of my procedure is that close to f star. That's bias. That's how well can I do on average over the data. Can I even approach f star? And this is a variance. How does this red curve vary as I draw different y's? Okay? And that's a tension. And also note that this is equality. Everything up to this point is equality. We started with what we want, which is the prediction error versus the best you can ever get. And we've got to a bias variance decomposition.
Why did you condition on the x's? I mean, what was I mean, you could have kept the expectation the same.
Over S? Why did I not do over S? I could have done that for this decomposition. That's another way of doing it. In the two applications, k-nearest neighbors and Nadarai Watson that we're going to do, we're going to use this form. But indeed, you could do expectation over S, and you would get a similar, the same decomposition, except you would get expectation over S here. Right. Okay, so now it's time to look at k-nearest neighbors. So where are we? We've done this, we've done that. Let's look at k-nearest neighbors. So what's the k-nearest neighbors procedure? you've got data, x1, xn, y1, yn. Their IID. Now, given x, I want to evaluate f hat of x, right? Because that's how I'm going to define my f hat. I'm going to give you a procedure that will give out a value on a new point x. To do that, I'm going to order, so how? Order x1 up to x n according to distance from the x. Okay, according to distance to x. Okay? So, I mean, the picture is very simple, right? I've got my data. So each one of these points is a pair xi with its value yi. Yi is, let's say, real, but could be binary if you want. And now if you ask me, what is the value here, then I'm going to order all the points according to the distance, and I'm only going to take the top k, or the bottom k, the closest k. Then I'm going to average their y values, and that's the output. Okay? That's the definition of the k nearest neighbor procedure. So I'm going to order that, and then f of little x is going to be the 1 over k. K is the parameter, so fix k, which is the parameter. And then I'm going to just order the y values that correspond to those nearest neighbors. So that's just y I from 1 to k, and I am assuming that x1 is the closest, x2 is the next closest, and so forth. Okay? Cool? Now, the typical thing that happens with local methods when you use this bias variance decomposition is that there will be a parameter. Actually, it doesn't have to be local methods. So whenever you do this bias variance decomposition, it's often the case that you have some parameter, and this term increases with that parameter, and this one decreases with that parameter. And now you have to balance them according to that parameter, and that's the optimal choice of the parameter, the one that balances bias and variance. Okay, so let's do this. So let's look at, right, so we're going to assume that f star is, let's say, 1 Lipschitz. 1 Lipschitz in the L2 norm. Why do we need to assume this? Well, you see, when we do k nearest neighbors, we're somehow assuming that whoever is close to us has the same y value. That's only true if the underlying phenomenon is somehow smooth or regular. And we have to capture that regularity. And the way that we're going to capture in this lecture is by a Lipschitz assumption that the function is the f star, the true phenomenon, the mean is a 1 Lipschitz function. Okay? You can consider other notions of smoothness. This is non-parametric.
So you cannot count any kind of statistical functions.
That's right. So this is a good point. This approach is different from, I'm going to set a class of functions, and I'm going to globally optimize fit to data. What's the difference, right? Imagine that the class of functions f is something like this, something like this. Okay, I'm being very hand-wavy. But the point is, if I've got data and I'm going to fit the best I can here, my choice of the function really has an effect here. It has a global effect. Because if I'm trying to fit the best I can in this part of the space, it will have a consequence here. Maybe my functions are like that, and they're really bad somehow. And by doing something here, I'm handicapping myself in some other part of the space. The local methods don't suffer from that. They are really local. The value at this little x only depends on the local neighborhood. You're more flexible, right? By doing something here, there's no kind of far-reaching effect on some other part of the space. Where you're minimizing empirical risk over some class of functions, that's a global procedure. And the analysis is different, and properties are different. If you're interested in neural networks, for instance, it's not clear what is the right analysis. Should they be analyzed as global methods that fit the neural network? Or are they flexible enough that what happens in this part of the space has no effect on the other part of the space? So maybe they should be analyzed as local methods, okay? And that's something to keep in mind, and I think that we're far from understanding that question. Other questions? So think of this global fit to data when you optimize over some class of functions is you set a set of models, and that's a very rigid set of models, whereas here it's much more non-parametric, flexible. Right? In this case, there is only one parameter, but in fact, it's infinitely many parameters, right? Because we're going to define, for each point, we're going to define a value. So you can think of this as a really non-parametric. There is no parameters here, right? We're not optimizing over some parametric family of functions. Okay. All right, so what's the analysis of this? So let's look at the variance term first. So what is the variance? The variance term is expected f hat. Well, let me go a bit slower. So what is f hat of x minus expected f hat of x? And again, what I'm doing here is actually I'm doing the same swap. That this is the integral over the little x, and this is the expectation. And what I'm going to do is I'm going to swap that integral and the expectation and look at the specific point x and bound that square for a specific point x. So this is the x, so fix x. Fix x. What is this difference? Well, let's look. So f hat of x is 1 over k sum of y I up to k. Now x is fixed. Okay, so the ordering is fixed. Now how about this? Well, that's minus the expected value of 1 over k y I 1 to k. And now these y's are conditionally on the x's, right? That's the reason we're conditioning on the x's. The ordering is the same, but the y values are different. But the order of distances to this point is still fixed, right? So now I can combine them. That's 1 over k sum of y I minus the I minus expected y I. Right. Now this is a zero mean random variable. What this is saying is the x's are fixed, so that we're working conditionally. x1 through xn. So the ordering is fixed. I'm going to redraw the y variables on average. Look at the average value minus the actual realized values. So each of these is zero mean. The average behaves as 1 over square root of k by the central limit theorem. I'm going to assume that y's are bounded for simplicity. So that behaves as 1 over square root of k. And so each of these terms is zero mean. So we're averaging k zero mean guys. So the average now behaves as 1 over k, 1 over square root of k. How about the square of this? Well, square behaves as 1 over k when you're averaging, right? The variance is 1 over k. So variance, which is the expected over the data set f hat and over x minus expected f hat of x behaves like 1 over k. Okay. So that's the variance term. Let's look at the bias. So the bias term is a little bit more tricky. So let's look at the bias. Let's look at the expected value of f hat of x minus f star of x. Again, fix x. And also let's fix x1 through xn. Okay? So we get the 1 over k sum of expected yi, right, minus f star of x. Now, what is the expectation of yi? F star of xi, right? So that's equal to 1 over k sum of a f star of xi. And we have to subtract f star of x. But because this is the average, I can bring the f star inside and just average the differences. Yes?
What's the expectation, like inner expectation, like variance?
This?
Like inner expectation?
This one is over the y variable, y1 through yn, right? That's this red. This red.
We're like these variables from S already? Like we have S, so
We have, and that's the dependence of f hat. But this is the average version of that. So you have to integrate over the hallucinated other y variables, right? That's the decomposition exactly. Right? But we assume that the function is Lipschitz, right? So now I have to put, in fact, the norms. So let me put absolute value. So that's equal to absolute value of that. That's equal to absolute value of that. And that's upper bounded by 1 over k sum I from 1 to k. If f star is Lipschitz, the difference of the values is bounded by the difference of the x's. Yeah? It's the definition of the Lipschitzness. X I minus x. Okay. All right, now I'm going to take expectations. So expected In fact, I really should have taken squares here. Square, square. So let me put a square here. Put a square here, nothing changes, nothing changes, nothing changes. And do I want a square? Just a second. Yeah, so I do want a square, so this is now upper bounded. Now by Jensen inequality I can pull out the average, right? Square of the average is upper bounded by average of the square by Jensen inequality. So I get 1 over k sum of xi minus x squared. I from 1 to k. Okay, this is just a high school algebra. And now I'm going to take expectations, right? So expected value of expected f hat of x minus f star of x squared. Let me do it over the data set S. Right. Is now upper bounded by 1 over k, sum of the expected x I minus little x squared over the data set S. Okay? So now I need to understand when I draw data x, x1, so I mean, this is, I can write this over x1, xn, right? When I have a little x fixed, and I draw n data points, what is the behavior of the average distance to the k closest neighbors? Anyone wants to guess? Let me ask the simpler question. I fix a point, and let's say that my domain is compact. So that's something I haven't written down, but let's assume that x's are supported on compact domain, right? So it's a bounded, let's say bounded set. So I fix a point, and then I draw in d dimensions, I draw n data points. What's the distance to the closest in expectation? What would you expect that to behave like? Is the question clear? So question, and I claim that it's enough to solve this problem. What is the expected over x1 through xn distance from a little x to the closest point? Is it clear?
Sample is large, n is large.
Yeah, so I want this as a function of, so it should be a function of n and also dimension. Turns out that for dimension 3 and higher, it doesn't depend on the underlying distribution.
If n is large, you're bound to have one that is very close.
Right, so how close?
I don't know.
That's what I'm asking. How close?
Epsilon can find, you can argue there is an n that would bring you to that epsilon.
Yeah, right. So I want a quantitative statement about this. It's not. I just want you to think about this a little bit. So let's say you had a box in d dimensions, and you look at the epsilon grid. What's the number of cells in this grid in d dimensions? 1 over epsilon. Okay, I don't care about the diameter. Let's say it's a unit. Okay. 1 over epsilon to the power d. That's the number of cells. So if my data points were kind of spread out, 1 per cell, then by equating this to n, I should roughly get the balance, right? When would I expect, if I could get a point in every grid, right? Then this is roughly what I would be expecting, right? The balance between epsilon, n, and d. So epsilon is something like n to the 1 over d, right? Minus. Yes, so that's true. So there is also the question about, is it L infinity boxes or, okay, but that's kind of inside here. That's going to be kind of a lower order effect. What is the geometry? But what's important is that it's a square. And because it's a squared, I need to square both sides. So this is what I would expect with endpoints, I would expect, if they really kind of spread out and fill the space, I would expect the closest one to be of the n to the minus 2 over d. This is a very kind of back of the envelope calculation. So the interesting result, and I'm not going to prove it, I'm just going to give you a reference in the slides, is that indeed this behaves as n to the minus 2 over d. For any distribution, in d greater than 3 dimensions. Interestingly, for 2 dimensions and 1 dimension, you need some assumption about the distribution, some mild assumption. I'll give a reference to that. The book of Devereaux does a good job. Okay, I claim that it's enough now to answer this question. Why is that enough? What's the meaning of this? Again, maybe keep expectation outside of this average. Maybe that's easier. So draw n data points and look at the square distances of the k closest. Let's do a mental experiment. Let me take the data set 1 through n and partition into j equal to n over k. Partition it into k buckets. Okay? So each one of size j. So this is bucket 1 up to bucket k. Anyone sees what I'm going to do now? So what I'm going to say is I'm going to say that this is smaller. So taking the data set and finding k smallest, closest to the given point, is upper bounded by taking the closest here, and the closest here, and the closest here, and the closest here. That's another way of getting k guys. But they're suboptimal because it could be that the k closest are all in one bucket. But that allows me to use this because I know that this is of size n over k, and if I get n over k, guys, the behavior of the closest is like that. So I get n over k to the power minus 2 over d. That's all. It's pretty nice trick.
This result is for any channels.
Yeah.
Because, like, for example, you have one the mass which is far from all of the other masses. And
It's a compact, so I'm hiding here, of course, the diameter, or some dependence on the diameter. I just care about the dependence on the dimension and the sample size.
Gaps or something.
You can have gaps in the distribution. There's not. It's for any distribution.
What's in this example? Because, like, whatever your n is, all the points that you sample are like with some distance from this point, because the mass.
But if there is a, if now remember that x is going to be a typical point.
Oh, okay, so you have the assumption that.
No, sorry. No, this x is going to be any point, right?
So what you're saying is that.
Okay. No, you're right. Okay, that's a good point. So, good point. So what I didn't do correctly is actually I need to average over x. So this x is typical. Yeah, you're right that I shouldn't be able to do it for an arbitrary, right? So I draw an x from the distribution, and I draw n points, right? Is that okay? Let me just fix this. So this is right, expectation over x and x. Please fix this. This is a good point. So there is x, which is drawn from the distribution, and there are n points, right? Yes.
I think if you want to lose like a little bit less, or like if you're okay with losing a little bit less, you can set like 1 represented d equals n log n, and then by like coupon collector, you're gonna hit every box.
Yeah.
So you can just like count it.
Right. Yes. So I'm being quite a bit hand wavy here. You can get a bit tighter dependence here. Exactly what you're saying. I can point to the tighter results on this.
So can you quickly go over the bucket idea again?
Yeah, so the bucket idea is I've got n points, and I've got my random x that I drew, right? The meaning of this quantity is that on average, what is the average square distance between k nearest neighbors to the given point? These k nearest neighbors could be in arbitrary buckets. They're somehow distributed here. But I'm going to upper bound it.
On the fact that each bucket will contain at most one of the.
And I'm just going to, no. What I'm going to say is that distance is smaller than if I take the closest here, the closest here, the closest here, and the closest here, because that's a suboptimal choice of getting getting k elements. But now I can use this result. Because I only care about the closest, the behavior of the closest out of a smaller subset of the data. So let me put these two together. Now I've got so conclusion, variance plus bias squared, it behaves like, so the variance is 1 over k, yeah? And the bias is n over k to the power minus 2 over d. And as I promised, is that true? Is that correct? 2 over d. Maybe there is a minus missing. Yeah, sorry. so this is correct. Right. This is correct. Right. So think of this as k over n to the power plus 2 over d. One term goes down with k, the other one goes up with k. If you balance these two terms, k equal to n to the 2 over 2 plus d balances. And the behavior then is n to the minus 2 over 2 plus d. So this is the final result. This is the behavior of, well, that the prediction error versus the best possible, the Bayes error. We've also written it as a estimation error in terms of L2P, and decomposed it into a bias and variance. The variance term goes down as 1 over k. The bias term squared behaves as 2 over k, n over k to the minus 2 over d, and that balances to that. Okay. So it's a slow rate, especially in high dimensions. This is a very slow rate. So k nearest neighbors is a slow procedure, but it works under very minimal assumptions. And this is consistent, right? This shows consistency. As n increases, dimension is constant, fixed. As n increases, you're going to get to the Bayes optimal. It makes sense. You're doing locally averaging. You're taking advantage of the Lipschitz behavior of the function, and everything works out. So notice a couple of differences, right? So we did not minimize empirical risk. We did not use uniform convergence. This analysis was really different from the uniform convergence analysis with the suprema over a class of functions, empirical minus expected, and so forth, right? Different approach. We've had some success analyzing kernel methods and neural networks using this machinery. So, it's worth knowing about this approach. Question?
Is the 2 over 2 plus d like true for all local methods? Like that's the behavior?
Yes. So if you start assuming more about the function f star, suppose it's smooth with higher degrees, so it's more smooth, then what you start getting is some blessing of smoothness divided by the curse of dimensionality. So if the phenomenon is very smooth, that can counteract the dimensionality. But for just Lipschitz, that's what you get. Yes? Without any assumptions, that's the best you can do. Yeah, this is optimal. Right, that's correct. If all you know is that the true regression function f star is Lipschitz, that's all you can do. Other questions? This is not the only method. I will show you next time the Nadaraya-Watson method, which gets the same rate, but it's a different method, and it's also worth knowing. All right, we'll see you on Thursday.